Now we move on to the second application of differential equations, which is Newton's law of cooling. It states that the rate of cooling of a hot object is directly proportional to its excess temperature above the room temperature at that instant, provided this excess is small. So here what we visualize is, suppose there is some hot object, say water is kept and it is heated. Let us consider that it is kept in a surroundings of temperature say theta 0, and we are heating the water or that object to some temperature say theta 1, and after that we are allowing it to cool, right? So now while cooling, let us consider the temperature at any instant to be denoted by theta, right? What Newton's law of cooling says that it's been observed that the rate of cooling, that is rate of drop of the temperature of the hot object, is directly proportional to its excess temperature over the surroundings. That means if you want to now write the differential equation, what we get is rate of change of temperature is nothing but d theta by dt, right? That is proportional to the excess temperature. Now excess temperature is nothing but theta minus theta 0, where theta 0 is the temperature of the surroundings or the room temperature. So therefore if you want to remove the proportionality sign, we will get d theta by dt is equal to minus k into theta minus theta 0. Now it's minus because the temperature of the hot body is falling down, it's decreasing. Therefore we have to take the negative constant of proportionality. Clearly this is also a variable separable type of differential equation. You see that theta is a function of time t. So therefore let us write d theta upon theta minus theta 0 is equal to minus k dt. So therefore on integrating both sides we get 1 upon theta minus theta 0 d theta is equal to integral of minus k dt. So therefore on integration we get log of theta minus theta 0, that equals minus kt plus c. You will see this goes on very much similar lines of what we got for exponential growth and decay. So here let us convert the log into exponential terms on the right side. So therefore we will get theta is equal to theta 0 plus e raised to c into e raised to minus kt. Now we know that initially, that is when t was 0, the temperature of the body was theta 1, because we obviously know what is the temperature to which we are raising the temperature of that body and then allowing it to cool. So therefore after we substitute that, we will get e raised to minus kt as 0. Therefore the value of the e raised to c will be equal to theta 1 minus theta 0 initially. So therefore on substituting we will get the final solution of this particular differential equation as theta is theta 0 plus theta 1 minus theta 0 into e raised to minus kt. So that's the general solution of Newton's law of cooling. If you see the term theta 1 minus theta 0, that is the excess temperature in the beginning, right? When the cooling started, the initial surplus temperature was theta 1 minus theta 0, right? That is getting multiplied by an exponentially decreasing quantity. So therefore the second quantity is continuously decreasing, and hence as a whole the temperature of the body will also go on decreasing with time. Right, now let's solve one example based on this. Alright, here is a question. A body cools from 80 degrees Celsius to 50 degrees Celsius at room temperature of 25 degrees Celsius in 30 minutes. Find its temperature after 1 hour more. Right. So if you show it diagrammatically, here T is equal to 0, that is the cooling started. Then in 30 minutes we can denote it as half an hour, that is a smaller quantity. The temperature reduced from 80 degrees to 50 degrees. And now we have to find out after 1 hour more. That means after 1.5 hours from the beginning, that is T is 3/2 hours, what is the temperature? And the temperature of the surrounding is given to be 25 degrees Celsius. So now let us write the general solution and fill in the details. We know that general solution of Newton's law of cooling is given by theta is equal to theta 0 plus theta 1 minus theta 0 into e raised to minus kt. Therefore, for a given situation we have theta is equal to 25 plus 80 minus 25 times e raised to minus kt, that is theta is equal to 25 plus 55 into e raised to minus kt. So this is the general solution for this specific question. Right. Now let's make use of the given condition, that is it's given that the body cools from 80 degrees to 50 degrees in 30 minutes. So that means at T is equal to 1/2, the temperature had dropped to 50 degrees. So therefore we can write 50 is equal to 25 plus 55 into e raised to minus k upon 2, because T is 1/2. Right. Now simplifying further, we will get e raised to minus k by 2 equal to, when we bring 25 on the left side it becomes 25, and that further gets divided by 55. So therefore we will get e raised to minus k by 2 as 25 upon 55, which is nothing but 5/11. So therefore we got an important piece of information, that is e raised to minus k by 2 is 5/11. Again, here it's not needed really to get the value of k as such. We'll keep this quantity and adjust it later. Alright, now we have to find the temperature after 1 hour more. That means at T equal to 3/2, what would be the temperature? So therefore let us write the general solution once again. We have theta is equal to 25 plus 55 into e raised to minus k into, now here T is 3/2, which we can write as 25 plus 55 into e raised to minus k by 2 the whole cube. This is because we already know what is the value of the expression e raised to minus k by 2. So on substituting that, we will get 5/11 the whole cube. Right. Now this is mere calculation. When we calculate this, we will get the final value to be approximately equal to something like 30.1 degrees Celsius. Right. So that's the answer of this particular question.